These are your 1-6 notes on relations. We're going to talk about the coordinate plane. We're going to talk about a relation and how to represent it as a set of ordered pairs, tables, graphs, and mappings. Pretty easy day, just a lot of vocab today. So let's get started. The coordinate system is a plane formed by the intersection of two number lines. The horizontal one is the x-axis, and the vertical one is called the y-axis. I think most of this will be review. Ordered pairs are a set of numbers, which we call coordinates, written in the form x, y. I do require that you put a comma between these two numbers and that they are enclosed with parentheses. That tells me that you are listing a set of ordered pairs, that you're telling me a spot on the coordinate plane. So I will mark you down if you don't have those two things. The x-coordinate is the horizontal placement of a point, and the y-coordinate is the vertical placement of a point. So down below here, I have a picture of the coordinate plane. Okay, and you can see that this is your x-axis. It's a horizontal number line. It goes from negative infinity to positive infinity, from left to right. It has all the real numbers on it. And then you have the y-axis doing the same thing, just in a vertical pattern. Going from positive infinity is up to negative infinity is down. Where these two lines come together is the ordered pair 0, 0, which is called the origin. So if I wanted to put a ordered pair 3, negative 4, 3 is my x motion. I would go 3 to the right, and then I would go down 4. There's my y motion, and here's the ordered pair 3, negative 4. That's how you plot points on the coordinate plane. You don't have to draw the arrows, but the end result of moving 3 to the right and down 4. A relation is a set of ordered pairs that can be represented as a table, a graph, a mapping, and an equation. We also just write them as a set. So if you would scroll your eyes down to about halfway down your page where this R is, that's a relation. It's just a set of ordered pairs. They can be random, they could be a pattern. Okay, so we usually use a capital script letter for that. We have the domain is a subset of the relation. So the domain takes all of the x coordinates in a relation. We also call that the input or independent variable. So domain is your x coordinates, and then your range is the y coordinates, and we also call them the output or the dependent variable. So you input x into a function, and then it will spit out a y value. Let's say I input the hours I work into a function, I multiply by my hourly wage, and the output would be my salary. That's sort of the idea between input, output, independent or dependent variables. Lots of vocab there. So let's look at the relation in different ways. The relation as a set of ordered pairs. So this is a set of ordered pairs. That's one way. I guess it says it right there. So you just use those little squiggly brackets to write them as a set of ordered pairs. As a table, you take your domain value. So here's your domain. Those are all your part of your domain. 1, 3, 0. And then your y values are all your range values. So you just put them in a table. 1 goes with 2, 3 goes with 1, and 0 goes with negative 2. If you want to represent relation R as a graph, you plot those points. So I'll go over 1 to the right, up 2. There's 1 point. Over 3 to the right, up 1. And 0, down 2. You do not connect them. There's a reason we connect dots in algebra, and it's not to draw a picture. These are unrelated. There were 3 ordered pairs in the set. There are 3 ordered pairs in the table, and there are 3 ordered pairs on the graph. This is a mapping. This first oval represents all the domain. The second oval represents all the range. So I'm going to put a 1, a 3, and a 0 here. I'm going to put a 2, a 1, and a negative 2 over here. You can put them in any order, but because I put them in the same order that they are, my arrows will not crisscross. Now, if I wanted to put them in order from least to greatest, I might have had some crossing arrows. So as long as my arrow from 1 goes to 2, 3 goes to 1, and 0 goes to -2, my mapping is correct. So here are some examples. Express relation T as a table, a graph, and a mapping, then determine the domain and range. So just a repeat of what we just did. So for T, my table would be 3, 2, -1, 4, 0, -3, and I accidentally left off a spot, -3, 4. Need to add on an extra cell there. For my graph, I'm just going to graph those. So over 3 to the right, up 2 would be my first ordered pair. 1 to the left, up 4. I don't go 0 left or right, down 3. And then to the left, 3, up 4 for that last ordered pair. 4 ordered pairs in my set, 4 in my table, 4 dots on my graph. And then for my mapping, now I've got 3, -1, 0, -3. And those numbers go to 2, 4, and -3. I'm not going to write 4 again because it's there. So this number goes to 4 and this number goes to 4. That just means I'll have double arrows pointing to 4. You can reuse numbers. In fact, we want you to reuse numbers. So if the number repeats itself, you only have to write it down once. So 3 goes to 2, draw an arrow. -1 goes to 4, we draw an arrow. 0 goes to -3. And -3 actually goes up to 4 as well. So there's your mapping. For the domain, it's all of your x values. So it's in set notation. I can just look at my table here. 3, -1, 0, -3. There's my domain. I could use my table, I could use my mapping, or I could just look up here and write down all of the x values. For range, same thing. My range is 2, 4, -3. I really don't need to say 4 again. You're just listing all the numbers in the range. I already listed 4. Got it. You don't have to read it, write it again. I won't mark you down if you write it again, but it's a little redundant, and I want you guys to work towards not writing it down. Okay, so now we're going to work with that independent or dependent variable input-output thing. Independent variables will not change because of the other variable, but a dependent variable could change depending on the independent. So in these two scenarios, we have two different pieces of information. The first thing you have to do is identify what are your things that vary. The cost of going to the movies has increased over the years. So the two things we're comparing here is the cost and years. Those things are varying. Obviously the movies are, but that's not going to have anything to do with this. So the two things we're comparing are cost and years. So you have to ask yourself a kind of a confusing question. So there's two different things. Could the cost of the movies depend on the year? Or does the year depend on the cost? If you write these two concepts down or just say them in your head as you're doing your homework, one will sound ridiculous. Could the cost depend on the year? Yeah. I think the cost of the movies in 1950 are much different than going to the movies in 2017. So I'm going to say that this one's true. If you read the second sentence, it sounds a little ridiculous. Could the year that we're in depend on the cost of the movies? So if the movies raise their prices, are we going to warp into the future? Or if they drop their prices, are we going to go back in time? No, this is a little ridiculous. So if you, again, identify the two things that you're comparing, list them both out with that depend statement, one's going to sound ridiculous. So now you just have to identify which one's which. Well, it says it right here. Cost depends. So cost is my dependent variable, and years is my independent. If you look at part B, same thing. As the temperature rises, the sales of winter coats decreases. We are comparing temperature with sales. So we write a depend statement. Does temperature or could temperature depend on sales Could sales depend on temperature? So the temperature outside depend on the sales of coats? That sounds a little ridiculous. The more sales we have of winter coats, is it going to get cooler and cooler out or hotter and hotter? No. But could the sales increase depending on if the temperature is rising or dropping? Absolutely. So sales depends. So the sales is the dependent variable. Temperature is the independent. That's what's driving the sales. We're also going to do a little bit of identification between the variables and actual graphs. So when you look at this, you got your two variables on your x and your y. Okay, x is always your input. It's also your independent. So time is independent of distance. This is your output, and that's your dependent variable. So if we look over time, as time increases, as the time goes up, so does the distance. The distance over time goes up, right? We can talk about in the beginning, it was a big spike, right? So from that section, there was a big increase in the distance, very little time. Then it's sort of the distance levels out, right? And then it's a gradual change. So we just described that. Distance increased by a lot at first, then leveled out. There's a gradual increase in the ends. In the second example, as time increases, income is increasing. And that's really all you have to say. As time increases, the income also increases. Now, if it decreased, we would say that. But as the time goes to the left, that's going up, or I'm sorry, to the right, and so is the income is going up. Your lesson summary here, give another name for the x-coordinate of a relation, and then I want you to write that mapping as set notation. So for the second one, we didn't really practice that. This is what they always gave us. Give me the set of ordered pairs there. Good luck.